There is a quiet assumption that sits beneath almost everything that we believe about the world. It is so deeply embedded in our thinking that we rarely notice it, and yet it shapes how we interpret every object, every event, everything that we experience. The assumption is simple. Things exist independently, and they influence one another through space in very predictable ways. A cup sits on a table whether you're looking at it or not. A signal travels from one point to another, never faster than the speed of light. Objects are separate and distance is real and tangible. For centuries, this assumption wasn't just philosophy, it was physics. Classical physics, as we now call it, built on the work of Isaac Newton, described a universe that behaved like a vast but precise machine. Every object had a definite position, a definite velocity, and a future that could, at least in principle, be predicted if you had enough information about the present. Reality was stable, it was local, and it was understandable. Then quantum mechanics arrived and dismantled all of it. Our entire assumption of reality was completely broken, and this new version of reality terrified even the most brilliant of minds. This is the theory of quantum entanglement. So at first, the cracks appeared small. Tiny particles like electrons and photons refused to behave like solid objects. They didn't follow clear paths or settle into definite states. Instead, they existed in something far more unstable, a condition known as superposition. Before being measured, a particle doesn't have a single fixed property. It exists as a range of possibilities simultaneously. What this means is that reality, at its most fundamental level, is not composed of solid things, but of unresolved potentials. So this is really where intuition begins to fail us. In our everyday life, uncertainty is usually a reflection of incomplete knowledge. You flip a coin and you cover it before looking at the result. The result is still already determined, you just don't know it yet. But with quantum mechanics, the coin exists in a state of both heads and tails until you measure it. This alone is strange, but it's not what breaks reality. This is only the beginning, to be frank. The real reality breaking begins when two of these quantum particles interact with each other. Under certain conditions, when particles come into close contact or are created together, they sort of merge. Instead of having separate states, they become part of a single shared system. In quantum mechanics, this system is described by a joint wave function. It's a mathematical object that contains all possible outcomes for both particles at once. At this point, something subtle but very profound happens. The particles are no longer independent entities. They're different expressions of the same underlying system, and this phenomena is what we call quantum entanglement. To make sense of this, we have to lean on some analogies. One of the most common analogies is the idea of a pair of gloves. If you were to place one glove in a box and send it across the world while keeping the other glove with you, opening your box immediately tells you what is in the other box. If you see a left glove, the distant box must contain the right glove. And there's nothing mysterious about this. The outcome was determined from the beginning. But entanglement doesn't behave like gloves. In the quantum case, neither particle has a predetermined state while traveling, and there's no hidden label attached to each one. Before measurement, both particles exist in superposition. They are not secretly decided, they are genuinely unresolved. And yet, when you measure one, the other responds instantly. If one particle is observed to have a specific property, such as spin up, the other will immediately take the corresponding opposite state, even if It is separated by vast distances, and there's no delay to this. It's not a signal traveling from one particle to another through space. The correlation appears to happen with no time passing at all. So this is where the structure of reality begins to fracture. Because this behavior violates something deeply embedded in classical thinking, local realism. The idea that objects have definite properties and that any influence between them must travel through space over time. Entanglement rejects both parts of that idea simultaneously. It tells us that particles do not have definite properties until they're measured. And it tells us that the outcome of one measurement can be linked to another across any distance, without any observable transmission of information between. Albert Einstein found this deeply troubling. So much so, in fact, that he referred to it as spooky action at a distance. Not as a poetic description, but as a frank criticism. To him, it signaled that quantum mechanics was incomplete, that something essential was missing from the theory. If entanglement were true in the way quantum mechanics described, then reality itself could not be built from independent parts. It would mean that separation, the very concept of distance, might not be fundamental to reality. Two objects could behave as one system, regardless of how far apart they appeared. And this introduces a contradiction that is very difficult to resolve. Because everything about our perception as humans is built on separation. You experience the world as divided into objects. Each object has boundaries, each existing in its own location. You rely on the assumption that what happens here is independent of what happens elsewhere, unless something physically connects them. Entanglement suggests that this assumption is not just incomplete, but also fundamentally wrong. It implies that at the deepest level, reality is not made up of things, but of relationships. This shift is subtle, but it carries significant consequences. If two particles can form a single system across space, then space itself begins to lose its meaning as a separator of objects. From this perspective, the universe doesn't consist of isolated objects interacting across empty space. It consists of interconnected systems that only appear separate when observed at a certain scale. And this is where the discomfort deepens, because it suggests that the world that we experience, the stable, predictable, object-based reality, is not a foundation of existence. It's a simplified version, a Coles Notes, an emergent layer that hides the deeper structure beneath it. And that is a structure where independence is an illusion, where properties do not exist until they're measured, and where 2 points in space can behave as if they are not separate at all. So at this stage, it is tempting to interpret entanglement as a kind of hidden communication, an invisible signal passing between particles that travels faster than light. But this interpretation quickly collapses under close examination. Because while, yes, the correlation is instantaneous, it can't be controlled. When you measure a particle, the outcome is completely random. You can't choose whether the particle is up or down. And because you can't control the result, you can't use it to send information from one point to another. And this creates a strange limitation. The universe allows for perfect correlation across distance, but denies any ability to use that correlation for communication. It connects outcomes, but not intentions. The result being a system that appears to violate the very structure of space while still preserving the rules of causality. This balance is not intuitive. It doesn't resemble anything in everyday experience, so it feels incomplete. as if there should be an underlying mechanism that explains how that connection works. For decades, physicists believed there must be. Einstein proposed that hidden variables, unseen instructions embedded within the particles, determined their outcomes in advance. In this view, the randomness of quantum mechanics was only apparent. Particles already knew what they would become when they were measured. And this theory would restore order to the system. It would preserve locality. It would allow reality to remain structured in a familiar and comforting way. But it also comes with a cost. It required accepting that the universe contained deeper layers of information that were fundamentally inaccessible, hidden beneath the observable world, and for a time, this seemed like a reasonable compromise. Well, until it was finally tested. What followed would not just challenge Einstein's intuition, it would destroy it entirely. There was a period in physics where the strangeness of quantum mechanics could still be dismissed as temporary confusion. It was assumed that with enough refinement, the theory would eventually reconcile itself with common sense, that the universe at its core would still obey the principles that had guided science for centuries. And those principles wouldn't be arbitrary. They formed what is known as local realism. Realism is the belief that physical properties exist independently of observation. A particle has a position, whether you are measuring it or not. A system has a state even when no one can see it. Reality is objective, stable, and external. Locality is the constraint that nothing can influence anything faster than the speed of light. Causes propagate through space over time. No effect can appear instantaneously at a distant location. Together, these ideas form a coherent picture of the world. Objects exist, and they interact through signals. Space separates them, and time governs their influence. Well, quantum mechanics threatens all of that. Einstein understood this immediately. His discomfort with entanglement wasn't about mathematical elegance or philosophical His discomfort with entanglement wasn't about mathematical elegance or philosophical preference. It was about preserving the structure of reality itself. If quantum mechanics were correct as it stood, then either realism or locality, or even both, had to be abandoned wholesale. In 1935, Einstein, along with Boris Podolsky and Nathan Rosen, formalized this concern in what became known as the EPR paper. The argument was very carefully constructed. It did not attempt to disprove quantum mechanics outright. Instead, it aimed to show that the theory couldn't be completed, that there must be an additional variable hidden beneath the surface that restored a definite reality to the systems that we observe. And you know what? The logic was straightforward. If two entangled particles are separated by a large distance, and measuring one instantly determines the state of the other, then one of two things must be true. Either the measurement sends a signal faster than light, violating locality, or the second particle already had that state before the measurement took place, preserving locality but requiring hidden variables. Einstein rejected the first option entirely. Anything being faster than light would contradict his most famous and successful theory of relativity, so he concluded that the second option must be correct. The particles must carry predetermined instructions that dictate their outcomes. These hidden variables would explain the correlations without requiring any spooky interaction. They would restore realism and maintain the integrity of space, and for decades this remained an unresolved debate. Until Niels Bohr, one of the founding figures of quantum mechanics, argued against Einstein's position. He claimed that the act of measurement is not a passive observation, but an active process that defines the properties of the system. According to Bohr, it is meaningless to talk about a particle having a definite state before it is measured. The question itself is just invalid. And this wasn't a disagreement about data, it was a disagreement about what the data meant. And for a long time, there was really no way to decide between them. You picked one side or the other. But the turning point came in 1964, when an Irish physicist named John Bell found a way to translate this philosophical conflict into mathematics. Bell's insight was deceptively simple. If hidden variables exist, they cannot produce arbitrary correlations. They are constrained by certain statistical limits. There is a maximum strength to the correlations that any local hidden variable theory can produce. This limit became known as Bell's inequality. Quantum mechanics, however, predicted something different. It suggested that entangled particles could exceed this limit, that their correlations would be stronger than any pre-programmed set of instructions could allow, and this created a very clear test. If experiments obeyed Bell's inequality, then Einstein's intuition was correct, and hidden variables existed. If they violated it, then local realism, the foundation of classical thinking, would have to be abandoned. For the first time, the question was no longer philosophical, it was empirical. In the 1970s, the first experiments were conducted. They were technically difficult, requiring precise control over entangled particles and their measurements, but the results were consistent. Bell's inequality was violated, and it has been violated in every increasingly refined experiment since. This result carries a very specific and very clear implication. It doesn't simply suggest that quantum mechanics is correct. It eliminates an entire class of possible explanations. It proves that local hidden variables, the last refuge of classical intuition, do not exist. The particles aren't following pre-written instructions. They're not secretly determined in advance. And yet, their outcomes remain perfectly correlated. And this leaves only one conclusion. The universe is non-local. Non-locality doesn't mean that information travels faster than light in any usable way. It means that the concept of independent localized objects breaks down at the quantum level. Entangled particles are not separate entities exchanging signals. They are components of a single system, regardless of distance. From this perspective, asking how one particle affects the other, it's the wrong question. There's no influence traveling between them because they aren't two independent things to begin with. There's only one system expressing itself in two locations. And yes, this is difficult to accept because it conflicts with how perception is structured. Human experience is built on the idea that space divides objects, that distance creates independence. Well, non-locality suggests that this division is not fundamental. It suggests that separation is, in some sense, an emergent feature, not a basic one. And this creates a deeper tension. Because if space does not fundamentally separate things, then what does it mean for anything to be somewhere? What does location represent if the underlying system is not confined by it? And these questions do not have intuitive answers. They force a shift away from thinking in terms of objects and towards thinking in terms of relationships. In classical physics, relationships are secondary. The object exists first, and relationships describe how they interact. In quantum mechanics, relationships come first. The system exists as a whole, and what we call objects are derived from how the system is observed. This inversion is subtle, but it changes everything. It means that knowledge of the whole doesn't translate into knowledge of the parts. As Leonard Susskind points out, you can know everything about an entangled system and still know nothing about its individual components. And it introduces a form of ignorance that can't be resolved. No matter how precise your instruments become, the individual particle remains undefined until it's measured. In quantum mechanics, reality is partially constructed through interaction. The act of measurement doesn't reveal a pre-existing state, it brings a state into existence. And once you accept this, you start to see its implications way beyond physics. Because it suggests that what we call reality is not a fixed structure, but a process. A continuous unfolding of interactions that define properties in the moment that they're observed. This doesn't mean that consciousness creates reality, as it is often misinterpreted. Measurement in physics doesn't require a human observer. It can be any interaction, any exchange of energy or information between systems. But it does mean that the idea of a fully independent, observer-free reality becomes difficult to maintain. Now the question is, how does a universe built on probabilities, non-local connections, and undefined states give rise to solid objects, stable identities, and predictable cause and effect relationships? The answer lies in a process called decoherence. At its core, decoherence can simply be expressed as the dilution of quantum entanglement. It describes what happens when a delicate quantum system interacts with its environment. Instead of remaining isolated, the system becomes entangled with countless surrounding particles, air molecules, thermal radiation, and electromagnetic noise. Each interaction spreads the quantum information outward, distributing it across a vast number of degrees of freedom. What once was a clean, isolated superposition becomes entangled with the environment in such a complex way that it can no longer be observed as a coherent whole. The system doesn't lose its quantum nature, it just becomes too entangled to track. Think of it like trying to hear your friend whisper in a crowded room. The original signal is still there, but it's completely overwhelmed by the background noise. This is exactly what happens to quantum systems in the real world. Entanglement, rather than being rare, is actually ubiquitous. Everything is constantly interacting, constantly exchanging information, constantly becoming entangled with everything else. But because this entanglement spreads so quickly and so widely, it loses the sharp correlations that make quantum effects noticeable. At large scales, the chaotic web of quantum interactions averages out into stable, classical behavior. Objects do appear to have definite positions, systems behave independently from one another, and cause and effect seems local and, thankfully, continuous. This is why physicists are able to observe entanglement in controlled laboratory environments. By isolating systems from environmental noise, they temporarily prevent decoherence from washing out the correlations. But outside of these conditions, the environment dominates. This means that the classical world is not a separate layer of reality, it is a byproduct of entanglement spreading beyond our ability to observe it. And this reframes how we understand separation. Because if everything is constantly interacting, constantly becoming entangled, then the boundaries between objects are not fundamental divisions, they're approximations. They're useful distinctions that emerge from complexity, but not from the underlying structure. At the quantum level, the universe behaves less like a collection of independent parts and more like a continuous system with shifting correlations. There's a tendency to treat quantum entanglement as a technical problem, something confined to laboratories, equations, and abstract models of particles that behave in ways disconnected from human experience. But this separation is misleading, because the real disturbance of entanglement is not what it does to physics, it's what it does to the human experience. For most of human history, reality has been treated as something stable, external, and ultimately understandable. Even when phenomena appeared complex, the assumption remained that beneath that complexity was a coherent structure governed by very clear and definite rules. The goal of science was to uncover those rules and translate them into a form the human mind could grasp. Quantum mechanics disrupts that expectation by undermining the framework that makes reality feel interpretable. It reveals that the categories that we rely on, that's object, location, state, cause, All of these things are not fundamental to reality. They are approximations that emerge under very specific conditions. Entanglement makes this especially difficult to ignore, because it introduces a form of connection that cannot be reduced to interaction. It shows that systems can be fully defined as a whole while remaining undefined in their parts. That knowledge doesn't necessarily decompose into smaller, more manageable pieces. This contradicts a basic assumption of understanding itself, the idea that to understand something is to break it down. In classical thinking, reduction works. Complex systems can be analyzed by studying their components. If you understand the parts, you understand the whole. But entanglement reverses the logic. The whole contains information that the parts don't, which means that certain forms of knowledge are inherently non-reducible. They can't be simplified without losing what makes them accurate. This creates a subtle psychological tension, because the human mind is structured to seek clarity through division. It isolates variables, defines boundaries, and builds explanations by separating systems into discrete elements. Entanglement resists this process. It presents a structure where separation obscures rather than clarifies. And this is where the discomfort begins to extend beyond physics, because it suggests that the limitations are not only in the theory, but in the way the mind approaches reality. That there are aspects of the universe that cannot be made fully intuitive because they are incompatible with the frameworks we use to understand them. The brain evolved to handle environments where objects are large, interactions are local, and outcomes are relatively stable. It developed shortcuts that prioritize efficiency over accuracy, and these shortcuts work, for the most part, because at the scale of everyday life, they produce reliable results. But quantum mechanics operates outside of that domain. It exposes a layer of reality where those shortcuts fail us, where the assumptions they rely on don't apply, where intuition, instead of guiding understanding, actively interferes with our understanding. This is why even highly trained physicists often describe quantum mechanics in terms of what is not. It's not classical, it's not local, it's not deterministic. That language reflects a kind of boundary where the goal isn't to make the system feel natural, but it's to describe it accurately despite its resistance to intuition. And this creates a shift in how knowledge is experienced. Understanding becomes less about forming a clear mental picture and more about accepting a structure that cannot be fully visualized. The equations remain consistent, the predictions remain reliable, but the interpretation is incomplete in a cognitive sense. This is where the idea of reality begins to change, not necessarily in its behavior, but in how it can be known to us. Because entanglement suggests that there may not be a single observer-independent description of the world that is both complete and intuitive. That different frameworks may capture different aspects of the same underlying system without fully overlapping. That any description of reality is filtered through the tools used to construct it, whether those tools are mathematical formalisms or cognitive models. All of this leads to a quieter implication. That certainty, as it is commonly understood, may not be achievable at the deepest level because reality does not conform to the structures that make certainty possible. In classical physics, certainty comes from determinism and locality. If you know the initial conditions and the laws governing the system, you can predict its future. In quantum mechanics, even complete knowledge of the system doesn't yield definite outcomes for individual events. You can know everything about the wave function and still only be able to predict probabilities. This doesn't arise from ignorance, it's a feature of the system, and it forces us to redefine what it means to truly know something. Knowledge becomes statistical rather than absolute, predictive rather than definitive. Instead of revealing a fixed structure, explanation becomes a way of navigating this uncertainty. It provides constraints, patterns, and relationships, but not final answers in the classical sense. Thankfully, though, this still does have a stabilizing effect, because while the foundation of reality may be uncertain, the emergent layer remains consistent. At the level of everyday experience, probabilities average out. Objects behave predictably. Systems follow patterns that can be relied upon. Yes, the instability is still there, but it's contained. This is why quantum mechanics doesn't disrupt daily life. It just doesn't need to. The classical world isn't false, it's just incomplete. It is a layer of approximation that works within a certain range of conditions, and within that range, it does remain valid. But entanglement reveals that this layer is not the foundation of the building. It's built on something else. The deeper you go into the structure of reality, the less it resembles the version that you experience. The more accurate the description becomes, the less intuitive it feels. And understanding that transition requires letting go of a specific expectation of the world. The expectation that reality should make sense in human terms. Because the history of physics has gradually moved in a very different direction. From a world that behaves like a machine, to a world that behaves like a system of probabilities, to a world that may be defined by relationships rather than objects. Each step along this process has reduced the role of our intuition. Each step has required accepting that the universe is not obligated to match the way it is perceived. Entanglement is not the final step in that process, but it is one of the clearest. Entanglement shows that separation isn't absolute, that properties are not fixed, that space may in fact be emergent, and that knowledge itself has limits that are not due to lack of information, but due to the structure of reality itself. The result is a shift in what understanding means to us. It becomes less about building a coherent picture and more about recognizing where coherence breaks down and what we can do about it. It's less about simplifying reality and more about accurately describing its complexity. And in that shift from one to the other, something does finally become clearer. The problem isn't that reality is broken. It's that the model that we inherited was never built to describe it at this level. Quantum entanglement doesn't destroy our reality, it just reveals that what we call reality was always just the surface. If you've enjoyed this video, then you'll definitely love our other videos on quantum physics. Click on the playlist showing on screen right now to watch all of them. Trust me, they all reveal a unique aspect of the quantum level that's even more fascinating than entanglement.